Hello everyone, welcome back. I hope that everyone is back. So what I can do is so that if more people are to join, then I can just go over first few slides again, and then we will continue. So the for 5 minutes, I will just repeat what we were discussing before. Okay, and the plan is for now would be to first finish with this looking at the ROP attack. Then afterwards, we will look at the format string exploit, and then we will look at the demo of format string exploit. After that, we are going to look at control flow integrity, and then finally memory bound checking approach for that. And if time permits, then at the end, access control. Uh, If you have any doubts from what we were discussing before, then please put them in the chat box. I can take questions now also, or you can ask them uh, whenever you get in doubt. Okay, so then my screen is shared and I think the recording is data. We are recording. Okay. So yeah, currently we are looking at return-oriented programming, ROP attack. And in the ROP attack, what we said that we are not going to execute some functions in the libc. We are going to uh, build a attack sequence, build a sequence of instructions using the instructions which are already present in your program. And let's say that if this is the attacker payload that the attacker wants to execute, then the attacker is going to use the instructions which are already present in your program to generate this attack payload. Now, how do the attacker do that? So to do so, there is something called gadgets. The attacker will try to find out these gadgets. So what is a gadget? A gadget is a short sequence of instructions which is followed by a return. And the condition is that so there are these two conditions. One is that the sequence is ending in a ret instruction, and then the another instruction is that these instructions, useful instruction, should not transfer control to outside the gadget. And then we looked at that how can we so then once we have these gadgets, once we have found out this sequence of instructions which are followed by return instruction, then we are going to so once we have, say, found these gadgets, so there we, if we look at the libc, then we would have found, say, over 10,000 such gadgets. Okay, over 10,000 such short sequence of instructions which are ending in red. And then in those gadgets that we have found, we will try to see, uh, like, can I form a gadget? So it is possible that the first instruction we can find, say, some gadget like that. The first instruction is there, and then there is red. In this example here, we have shown that all the gadgets here have only one instruction followed by red, but that's actually not how the gadgets will be. It can be any number of instructions here, okay? So it can be like if you do a binary analysis and you may find that these three instructions are as it is into your code followed by a red, then you can use that as first gadget. So then once we have found out these sequence of instructions which can be used to form these gadgets, so then we are going to stitch them together. Now to stitch them together means we have to call them in the order. We have to call these gadgets in the order so as that finally we have this code. So to do that, we will be placing the address of these gadgets on the stack. So when we are doing the buffer overflow exploit, we are going to replace the return address of the function with the address of the first gadget. And this return address is pointed to by ESP. And we discussed that the return instruction has these two steps. First, it is going to pop the content of the stack and store it into instruction pointer. And second, it is going to increment the ESP by 4. So then it's when this happens, when the function returns, it will read this address, which is the address of gadget 1, and then it is going to start executing from here. Now, when this gadget finishes and in the end the red instruction is executed, at that time it will pop the address from here because that is pointed to by ESP now, and then it will start executing from this address. Then the next red instruction will cause the next 4 bytes to be used as the address. That will be the address of the gadget 3, and that in this fashion we are able to stitch together these gadgets from the program binary to create a payload of the attacker's choosing. Here, the attacker has not added any code into the program, and the attacker is only modifying the storing the value of these, storing the addresses of these gadgets onto the stack. So only the buffer overflow vulnerability has been exploited here by rewriting the buffer beyond the bounds of the buffer, starting from the return address location. But no new code has been added into the program binary. And then we looked at that how can we find these gadgets. So we were saying that for this we'll have to do a analysis of the binary for the binary or the libc. And then in that libc, what we are going to look for, what in the binary, what are we going to look for? We are going to look for the instruction sequence that ends in the return. Okay. And then that instruction sequence must also fulfill the second condition, that none of the instructions in that sequence transfer the control out of the gadgets. So we are going to take our binary, and then we are going to start scanning this binary from the beginning, and then we are going to look for the uh, byte C3, because this byte C3 is the opcode for the return instruction. And if we find 0xC3 anywhere, then we are going to start scanning backward, and then we are going to look at each byte, and we are going to ask the question, is the subsequence forms a valid instruction? If it's a valid instruction, then we are going to add it as a child, basically we are going to add it as a valid instruction as part of our gadget. And if not, then we move forward. And so the work which was done by the paper, which is referred here, they were able to find 15,000 plus gadgets in the libc library. And then we talked about the intended and unintended instructions. So the compiler generates this machine code from your program, and then the compiler has created this byte sequence that is like the machine code in correspondence to the instructions, these assembly instructions. So for example, it is possible that if this is your machine code, and let's say that this is the intended instructions which the compiler intended to do. But if you start reading this machine code from this byte C7, and then you can interpret this machine zero double zero zero F actually forms a it is the opcode for another instruction, and that instruction is move L, this value into EDI. Then the next byte 95 is opcode for next instruction exchange, and 45 is opcode for increment, and C3 is opcode for ret. Note that here C3 was earlier not even used as a return instruction. And the paper talks about like that it's very likely to find such unintended instruction sequences in a x86 machine code because x86 provides a diverse ISA. It provides a diversity of instructions set compared to the RISC architecture where the instruction set is doesn't have this much diversity, and also the size of the instructions is fixed to say 32-bit in ARM 32. So there is no question. So then now we are going to actually start from here. Okay. So we are starting from here. So so far we just looked at what are these gadgets and how we find these gadgets. Now let us look at the examples of these gadgets and what can we obtain from these gadgets. Like what can we do with the gadgets? So we can load a constant value into a register with the help of the gadget. Okay, so let's say that you want to load the register EDX with value dead beef. Okay, so what you can do is that you can place your gadget address on the stack, and let's say that the gadget is of this type. The gadget that you have found is of this type, pop EDX and return. So what will happen is that when this gadget is called by using this gadget address, then your stack pointer would have been incremented, right? 2.2 here, dead beef value, and then this value will be popped into EDX. And then you return, and let's say there can be different address of the next gadget here. So in this manner, you can even store some value into the register. So you can store some value into this register in this manner. So so here let's see this. A previous return will pop the gadget address into EIP. Then the ESP will be incremented to point to deadbeef 4 bytes, and the pop EDX will pop the deadbeef from the stack and then increment ESP to point to the next 4 bytes on the stack. So with this gadget, you can load EDX register with other value of your choosing. Next is stitching these gadgets together. So here we have uh, so here we are going to try to load an arbitrary data into EAX register using gadget 1 and gadget 2. Okay. So let's say what we are trying to achieve is that let's say there is some data on your stack. Okay. There is some data on the stack, and you want to uh, basically you want to read that data, you want to store that data value into the register EAX. So this stack has this data value stored here, and now you want to store this dead beef value on from the stack into EAX register. Now how can you do that? So for this, let's say we are using these two gadget 1 and gadget 2, because why are we using two gadgets? It's possible that we may not, these are the two gadgets that we have found, and we have to use them, because when you have these gadgets, it's not always possible that you will find the exact code sequences that you need there. Sometimes you may have to change, use like functionalities from use different gadgets together to create your sequence, that the basically the functionality that you want from your sequence of instructions. So here we wanted to load arbitrary data into AX register, and maybe let's say we have these two gadget 1 and gadget 2, and we are going to try to use them. So first we are going to put we are going to here change the return address and set it to the address of gadget 1. Okay. After that, on the stack, we are going to put here an address ADDR, which is, let's say it is here, and then we put the address of gadget 2. So what will happen? Okay, so we have seen the how the stack content is. Now let's look at the gadgets. The gadget 1 is a pop EDX and then return. So it will pop the content from the stack and store it in EDX. And the gadget 2 is move 64 EDX, comma EAX. So it's going to move the content of the memory pointed to by EDX register plus 64 into EAX. And then it is going to return. So, so here, what we are doing is that when we have changed the address, return address to point to the address of G1, then when G1 starts executing, it is going to pop this address from the stack and it is going to store it into EDX and it is going to then return. When it returns, then this return address, which is this is going to be used as the return address. So address of G2 is used as return address, and then we start executing the gadget 2. Now EDX value is equal to ADDR. So ADDR plus 64, the value at this location is going to be moved to EAX. And ADDR, let's say it's here, and then plus 64 bytes away is our data of interest. Now, you like, why did we choose this ADDR uh, plus 60? Like, why did we use this particular address only? Like, why did I not use exactly the address of this location? So that is because we have the gadget 2 of this type. We have the instruction available in the gadget 2 is of this type only. If the instruction was say like move EDX, comma EAX, then we could have put directly the address of this location here. But since our instruction is of this type 64 EDA plus EDX, so that's why we have to use the we have to fill EDX with the address ADDR, which is 64 bytes away from the address of interest. Okay. So with this gadget, we are now able to store arbitrary data from the stack into the register EAX. Is there any question? Okay. Yeah, so we have been able to, in this way, we have been able to now load the content, load some value into the register. Now, let's see if we can store the content of a register to a memory location in the stack. So here we have these two gadgets. Okay, first one is this pop EDX and ret, and then the second one is move EAX to 24 comma EDX. Okay, and so sorry, it's a bit uh, like overlapped here. But what we have here is the gadget of the address of the first gadget. Then we have value 0 here. Then we have here 2 and then address of the next gadget. Okay, so first we are going to first when we return from the function, then the first gadget will be executed. The first gadget is going to pop the value from the stack, which is here is 0, and it is going to store it into EDX. And then it is going to return. And after that, it has the, then it is going to return. So I think this is actually, yeah. So this is now the address of the gadget second. So it's going to, so the first gadget is going to be invoked when the return address is read from the stack. Then it is going to pop the content of the stack, top of the stack, and put it into EDX. So 4 bytes would be incremented. When we start executing this gadget, your ESP would be pointing to value 0. After the pop operation, it will point to gadget address 2. So when we return, it is going to use the address of the second gadget from as the next address of the next instruction, and then it is going to start executing here. Now here, if the instruction is move EAX from comma 24 comma 24 plus EDX, then this is going to move the content of register EAX, whatever is stored in EAX, into this location, which is 24 plus EDX. And EDX here is set to value 0. So it is 24 plus 0, which is 24 bytes away from here. Okay, so if ESP is pointing, say here, then it will be 24 bytes away. So it is a base plus displacement addressing mode for here, and where EDX is the base address, and 24 would be the displacement. So then it will be stored 24 bytes away on the stack. So the you have so with this, with such a gadget, with stitching such gadgets together, basically you can store some value also on the stack. Next one is gadgets for addition. Okay, so how can you use the gadgets to do, say, addition operation? If you, so here, let's say that you want to add the memory pointed to by EDX plus EAX. So here in this gadget, we have first instruction is add L. So it is going to add the content of the memory pointed to by EDX uh, to EAX, to the content of register EAX. And then the register is also stored in EAX. Okay. Then it pushes the value of EDI onto the stack, and uh, so then it is pushing the value of EDI onto the stack. So now this is actually not necessary, because like for our gadgets, but this is the only, let's say, the best gadget that we were find, which was able to do addition. So then we will have to use only this gadget. Okay, so this particular example, what we are discussing, that how can we create a gadget to add two values. Okay, so let's say we found only this gadget, and then this gadget, the first instruction is to add the memory, a value of the memory pointed to by EDX with EAX, and the result is stored in EX. After that, there is instruction push EDI. But this instruction push EDI is actually not necessary here. But we did not find, say, any other gadget, and this is the only gadget. Now what's the problem is here is that it is going to uh, so if you have store, if you want to, say, call some other gadget after gadget ADDR after the first gadget, then this is going to uh, after the this push EDI, this gadget to value will be corrupted, because it would have pushed some value onto the stack, and then the address of the second gadget would be corrupted. So then when you will return and this value will be read, then it will not work anymore. So that's why we will then need a workaround for this. So we are basically trying to what we are showing like seeing with this example is that it's not always possible that there'll be gadgets exactly doing what we want to do, but then we can still create like we can still work around those and try to still do the the operation that we want to do. So the operation that we want to do here, which is of our interest, is, say, let's say it is the addition operation, and then followed by some other instructions. Okay, so how are we going to solve this problem that this gadget has this push edi instruction, which is pushing some content onto the that and therefore corrupting the address of the next gadget here. So to solve this problem, we are going to use another gadget, and this gadget is actually has only one instruction, which is the return instruction. Okay, and so then what we are, and so in when we talk about the return oriented programming, so at that time the gadget here the gadget containing only the return instruction, it is basically it would work like a NOP instruction in a ROP. So like first we put the gadget pointer for 0xc3 into EDI. Okay, so we are going to first put this 0xc3 the address of this gadget into EDI, because here we are pushing the EDI content on the stack. So we have found that the gadget, I think, which is of course is easy. It's just any byte sequence C3 location. So we have this gadget which contains only one instruction, which is the return instruction. What we are going to do is that we are going to now use one more gadget, let's say, and the gadget here is pop EDI. Okay, so it is popping the stack content into EDI register. So we are going to put the address of this gadget on our stack, and then followed by the address of the gadget uh, 0xc3. So what will happen is that when we return, then this gadget pop EDI return will be executed. It is going to pop the content from the stack, which is the pointer to the return uh, gadget here, and this value will be popped and stored into EDI. When it returns that the next gadget address, which is already placed here, it will be used. So then the control will be transferred to this gadget, which we were originally looking at, the add gadget. Now, when this add gadget executes, and after that there is a push EDI. Now the push EDI actually contains the actually contains the address of this ret gadget. Okay, so then it is going to push this gadget underscore ret. And we have placed the address of our gadget 3 after that. So we had, say, probably left this as blank, or maybe we could have put nothing here. So then this was filled with this push EDI. And when the control will be passed here, then it will just return and use this as gadget 3 address. So as you can see here, the gadget 0xc3 is basically doing nothing because it's just a return instruction. It is going to read the next 4 bytes as the return address, and then it is going to increment the ESP. So it does nothing. And it works like a no operation instruction in ROP gadgets, when we're in ROP gadgets, when we are stitching together these as a gadget in ROP, return oriented programming, it works like a NOP. So I will stop here and see if you understand this or not. So uh, please let me know if you have any question so far. Okay, there is no question right now. So then let's look at that how we can create a unconditional branch in ROP. Okay, so like we are basically trying to see if what we can do like with gadgets. So we were able to store a value into a register, okay, of our choosing using this gadgets. Then we were able to load some value from the stack into some register. We were able to store some value of our like pop edx, and here, yeah, we were able to store the content of a register into a memory location of our choosing on the stack. And then we are able to do addition also. And for here we just made this like this was just made complicated, and it was made complicated because there was this push edi instruction which is corrupting the return address of the next which is corrupting the address of the next gadget. And so then we saw the workaround this. And the next, now let's look at how can we create unconditional branches in return oriented programming. So so here, let's say that this is our gadget, which is of these two, consists of these two instruction, pop ESP and then ret. So what does pop ESP going to do? It is going to pop the content which is located at pointed to by the ESP, and then it is going to return. Uh, Actually, not so it is going to pop the content from the top of the stack, and then it is going to store it in the ESP. Okay, so if you have stored here, say your address of this gadget itself, so this is your gadget, okay, and you will store the address of this gadget here, and when the function returns, and this will read it as the return address, okay, and after that, mm, no, not with respect to the function return. Let's say this is pointed to by here ESP. This is your ESP, okay, or this is your gadget. And this value is what is being currently pointed to by the ESP. And this is the gadget address. So when this gadget address is used, then you are going to the control is transferred here. It is going to pop the content of the stack, and that value is popped into the ESP. So the ESP is currently pointing here, right? So the value is popped from the stack, and then it is pushed here. And then afterwards you will return. So the return instruction is going to again take this address, and then it is again going to pop it and then store it into the ESP. So in this way you will be able to create it as a loop, like it's an unconditional jump. So it's like a loop, okay? Because you're popping and then you're restoring it into the ESP. So that's why you keep reading the same value, you keep returning, and that's how it is like implementing a loop. So the gadgets can, of course, do much more. And we just looked at only few examples. And as I was saying, that there are, say, 15,000 plus such gadgets. And I think so it's like you can stitch them together and you can do arbitrary operations. As we just saw, that we can fill some register with an a value of our choosing. We can store the content of the register at the arbitrary location. We can read from arbitrary location on the stack. We can do operations like addition, and we can create loops, etc. So basically we can do anything with the gadgets. And so the gadgets have to be so these gadgets have shown to be Turing complete. So basically, you can do anything. The attacker can has the power to do anything by stitching together x86. So stitching together gadgets on x86. So the x86 instruction set architecture provides so many diverse instructions that the attacker can create these gadgets which can be arbitrarily stitched together to do anything. Okay, so the for the risk processor, it's more difficult to find such gadgets because the instructions are fixed length, and it's harder to find these unintentional instructions we were looking, because the instructions are of fixed length and then they are aligned. So there are some tools that you can go and look at, which automatically, if you will give them the source code or binary, then they will be able to find out all the gadgets that exist in that binary. So you can look at the gadgets, the tools such as ROP gadget or roper, etc., which are shown here, and then you can find these gadgets. Now I will stop here and take can I can take a question if there is any. So if there is no question, then we are going to. So here we have so far looked at return to libc attacks and ROP attacks. And these attacks, the return to libc attack was trying to use the functions which are there present in the libc, and the return oriented programming is more advanced than the return to libc attack, because it is ju- uh, not only using the code which is already part of your binary, but it is also creating this arbitrary code sequences by finding these gadgets and then stitching them together by putting the gadget addresses on the stack. So this is like a advanced uh, attack here, buffer overflow, an advanced exploit, which is exploiting the buffer overflow vulnerabilities. So far we have discussed buffer overflow vulnerability and the exploits which are using this buffer overflow vulnerability. And now we are going to look at the format string vulnerability and the format string exploits. Okay, so now we are looking at the format string vulnerabilities, and so this vulnerability it exists. So just to reiterate, actually, I have finished. So we have finished looking at buffer overflow vulnerability, and we have looked at the buffer overflow exploits. So if you have any question regarding that, then please feel free to put them in the chat box, and then I can take them from there. But now we will look at this actually the last class of vulnerabilities, because the next we are then going to look at only defenses. And so this is called format string exploits, and which are or and the vulnerability is called format string vulnerabilities. And the vulnerability actually here exists in your yeah, so this is being recorded and I will put this on YouTube. Yeah, so the vulnerability here is the format strings is in the printf or similar functions like fprintf, scanf, and this class of function library functions basically. And the vulnerability exists because let's look at that. So this class of function like printf function, it basically takes, and this is the function declaration for printf in your library. Okay, this is the function printf. It first takes this format string. Okay, and then it takes the variable arguments, like you can pass any number of arguments to printf, and here and first it takes this format string. Now what is a format string? The format string basically is going to specify that how the values should be printed on your say out, as the output. Okay, so this is the formatting. And so this format string, let's say for example here, is that it is the magic number is and percentage d per slash n. So here this complete itself is a format string, and the percent d here is the format specifier. The it is specifying that what's the value which is being printed. Like percent d here means that a decimal integer value is printed. And there can be other parameters here such as percentage u, percentage x, percentage s, and percentage n. So percentage u is means that the unsigned decimal or integer value is printed. Percentage x means print the value of the integer in hexadecimal notation, and percentage s is for printing the string. Okay, and then percentage n is to print the number of bytes written so far. Okay, and then percentage n here, why would we need something like this is so that the programmer can basically programmatically decide how the output should be printed. Okay, so let's say this is this format. So let's say the, like for example, the fprintf function, or so like in case of servers, they can be say you might be taking say a log of your server, and when you are storing into these log files, then you may want to store into the log file in some particular format. So this format string can specifies the format in which the different fields must be written, or basically how your output which is being generated is formatted. And then this log, let's say, which is being generated, then it will be parsed, or it will be analyzed for say inspection or something. So it's important that this log is formatted in a particular manner. And so many a times it happens that this format string is not always like as it is specified here in the first example that the format string is actually part of the it's like is part of the code. So as you can see, it's a double pointer, like a pointer to a character pointer. So it can actually even be passed as an argument. Okay. So you can take, say, an input from the user when you are starting the program, that how should the output be formatted, which is being stored in the log. So it can even be taken as an input. So the format string, what I'm trying to say here is that uh, it is not always the case that it's what you see, like usually we write this in our programs that this is the format string. But I'm saying is that it is also possible that even the format string is being taken from the user as an input. Okay, so in that case, so similar to the buffer overflow attack, the user can provide a arbitrary format string. Okay, and that's the first thing. Then after that, we have these arguments, and as we can see, that arguments is variable arguments. So you can provide any number of arguments here. So can you tell me, like, what will happen if you say uh, have these here percentage t comma percentage t. Let's say you have only 2 percentage t and you have only one argument, or you give here, say, two more arguments, but there is only 1 percentage t. Will your program give an error? Will it compile, not compile? Will it give a runtime error, or what will happen? Yeah. Yeah, so that is right. So if here you have 2 percentage t, and if you have only one argument, so you will you will not get any error. Okay, you will not get any compile, or you will not get any runtime error. Yeah, your both percentage t will print something. The first percentage t is going to print the value of the argument, and the second one is going to print some other value. So now we are going to look at, like, so that means you can there is no check on what the format string contains, right? There is no check how many arguments are being passed, or how many format specifiers are there. So let's say that this is your printf. Okay, the printf here is printf statement in your main function is this abc store %t %d %s, and then you have a, b, and c value. So let us see that the see at the printf invocation here, like how printf is going to work. So printf is this library function, right? So, so since it's a library function, so it is also like a function invocation from main, right? So what happens on a function invocation is we are going to first push the arguments to the function, right? So the argument to this function are what? So these are all the argument to the function, right? And as you just saw, the printf function takes these arguments. First is the format string, then it's the variable number of arguments, right? And so these are all the arguments. So we are going to push here C, then B, then A, and then the pointer to the format string. We're going to put the address of the format string. Okay, let's say this is your format string ABC store %d %d %s respectively, and then this will be stored there on the stack, and the pointer to this would be passed to your printf call. Okay, afterwards, after that, you are going to push the return address, then the previous frame pointer and the locals, and then the printf will start. So till here pointer to so till here it was the invocation of printf in main, and then main pushed the return address, and then it new frame was created for printf, and now you are here in the printf function. Now, if we look at this printf function implementation in the C library, so this is a very simplified, oversimplified, like say, implementation of the printf library function. But if we look at it, what it is doing here is that first here it is creating a list of the argument pointers. Argument, yeah, it is this list is the argument pointer. Okay, so here, yeah, so here we have these two different pointers. Okay, one is the pointer inside the argument, and the second is the pointer in the format string. Okay, so we are going to have these two pointers. Argument pointer means pointer into the arguments, that are variable argument that are being passed on the stack, and one is the pointer inside the format string. So here the argument pointer is initially pointing to A because these are the arguments, right, to printf, uh, like the arguments which have to be get for these format specifiers, and P is pointing to the beginning of the format string. Then there is this for loop, okay, and this for loop, initially P is in the beginning of the format string. In the for inside the for loop, we are going to check the value which is stored at this pointer. And if this like byte by byte, we are going to parse this. So basically, a printf function is like a interpreter. Okay, it is going to parse this byte sequence which is being passed here, and it is byte by byte, and then it is going to, based on what is being passed, it is going to take one of the actions. So if the value which is being if the byte sequence, if it finds that if it is a say percentage value, then after that what it is going to do is that it is going to look at, it is going to switch to one of these different cases, like whether it is it a D, whether is it a S, or which it is going to switch to the cases. Like if it is a D, then it is going to then that specifies that it is a the value which is stored in the argument, the value which is pointed to by the argument pointer is actually a integer. So it is going to treat that value which is being stored here as an integer and going to print it as is. Okay, if it sees that this is a S, then it is going to see the value which is pointed to by the argument pointer as an address, and then it is going to go to that, then it has this for loop which is going to start reading from this address, and then it is going to read until it finds a null character. Until the value becomes null, it is going to keep reading, and it is going to keep printing. So is there any question? So what we are looking at here is very simplified, uh, in a very simplified manner here, how printf function works in the C library. So you are going to pass here a format string, and you are going to pass the arguments, the variable arguments here, and the format string, and then in the inside the printf function, it is going to create like these two pointers. The first pointer is pointing to the argument string. Okay, not the arguments T. The first pointer P is pointing to the format string, and the second pointer AP is pointing to this argument list. Okay, the list of the arguments which are there on the stack. And then after that, it is it has this for loop. Inside the for loop, it is going to look at every character, and it is going to check the value of that character. So if the character is say any other value except percentage d, then it is going to keep printing. If it sees a percentage, not sorry, not d, if it sees a percentage character, then it knows that this is a format specifier, and then it will uh, look at the value, whether it is a D, X, U, S, etc. And if it sees say a D, then it is going to go to the case, switch to the case D, and it is going to handle it. Now to handle for percentage D, what it is going to do is that it is going to read the value which is pointed to by the argument pointer as it is, and it is going to print it. Similarly, for U and for say X, for X, it is going to print it as a hexadecimal value. So this is how it is working. And for S, which is a percentage S, so when you specify percentage S, what it is going to do is that it is going to take that argument which is stored here and use it as the address of that string, and then it is going to start a for loop to print starting from that address, and it will keep checking byte by byte until it encounters a null character. It is keep going to print from starting from the string start address. So this is how the printf function will work. And okay, so this is what I've already explained, but so when it sees the first percentage d, it is going to use this value. Okay, and then when it is sees the next percentage, and so when it sees the first percentage d, it is going to use this value, and then it is going to increment AP. Then the next, when it sees the percentage t, it is going to use the next p value and increment. And then when it sees this c, it is going to treat this as the address of the string. So let's say when we pass insufficient arguments to the printf function. So if this is the printf function, and this is the format string with, and it has these three format specifiers, percentage d, percentage d, percentage d, and then there are two arguments a and b. So we are passing only two arguments, and we have three format specifier. So the question is, can the compiler detect this inconsistency? Can the compiler detect that in the code, the programmer has, say, passed only two arguments and there are three format specifier? So if the compiler want to detect this inconsistency, that means we will need to build the compiler with the knowledge of this function, library function printf. Okay, and this will make the compiler library dependent, because the compiler will need to be made aware of the semantic of this printf function. And also, so that is the first problem. And then the second problem, as I was discussing earlier, that it is possible that this format string may be passed as input by the user, or it can be taken from a file or anywhere. So this format string may even be created at runtime, so it cannot be detected by the compiler. Second, can the printf function detect this inconsistency? So it's also not easy for the printf library function to detect this inconsistency. And why is it so? Because when we are passing, because the library function printf takes variable arguments. Okay, so it's not like that the library function is taking 3 arguments. So it can detect, okay, if I'm getting 3 arguments, then it's okay, and 2 is not okay. So it is taking these variable number of arguments, and when it uh, sees these format specifiers, it is just going to pick out the arguments from the stack whenever it sees a format specifier. So what is stored on the stack when the printf is called, whether it was a argument which it was passed to the printf, or whether it is just some garbage value which is already on the stack, that printf will not be able to distinguish between. Okay, so printf will not be able to distinguish whether the arguments which are stored on the stack, like what that was what whether that was actually intended to be passed, or it is just less number of arguments were actually passed to printf. So is that clear? So, so regarding your question, actually here the problem is happening because of this printf interface, right? So because in the printf we do not have a defined interface. Like it can take variable number of arguments. So you can sometimes pass 3 integer arguments, sometimes you can pass 2 integers, sometimes 2 integer, 1 string. So how can the printf function even know that what did you intend to pass? The only way it can know what you intended to pass was that it is doing with the help of these format specifiers. It's looking at the format specifier and then trying to figure out, okay, the first argument is meant to be an integer, the second argument is meant to be a string. So you cannot do the type checking because it's not specified here into the arguments. And it can also not check, like similarly, how many arguments are passed and then throw an exception when it does not have argument specified for like in match to a format specifier, because the printf function has like does not know how many arguments have been passed. Like you're not passing here a count saying, okay, I'm passing 3 formats, there are 3 format specifiers, and then I should pass 3 arguments. So it does not know. So if you have this printf call, it has 3 format specifiers, but printf function has no way of knowing that whether the function was invoked by pushing 3 arguments on the stack or not. Because when you invoke the function, you're going to push the arguments. You're going to push b, a pointer to the format string, and then when the printf function start function like running, it is going to parse this format string by, and then it is going to look at these format specifiers. For the first format specifier, it is going to read the value a, print it. Then for the second, it is going to print value of p, value which is stored here. And then for the third one, it is going to print what is written here. It has no way of knowing whether it was, when it was invoked, whether 3 arguments were pushed onto the stack or 2 were pushed onto the stack. Yeah, so is this question? And while it's parsing using the case statements, here, when it is parsing using the case statement, but it has the pointer to the first argument, which is, let's say, here. Okay, but it does not even know that how many arguments were pushed onto the stack when the printf function was invoked. So when you are parsing using these cases, you are only looking at these format specifiers. Actually, you're not have no knowledge of what is pushed onto the stack as arguments when this function was called. Okay, I hope that is clear. Does anyone else have confusion regarding this? That why this cannot be detected by the printf function or the compiler? Okay, so then go to the let's go to the next slide. So now we have learned what the problem is. So the problem is that the printf function is going to look at this format string, look at the format specifiers, and then it is going to print from the stack. Okay, but it has no knowledge or about like what is stored on the stack, whether how many arguments were passed to this function. So since it has no knowledge of this, and so you can create such a arbitrary format specifier, sorry, format string, which consists of these percentage s's, and then you can pass this. And note that here there is no argument at all. Okay, and when you call the printf function now, when this printf function is basically called by your say main function now, it is going to only push the address of this format string. Now, can you tell me what will be the output of this program, and why so? If you have this program, if you write the main function, add this and write this printf there with even say 1% s, you do not specify anything here, any format, any arguments, then can you tell me that what will be the what is the expected output of this program? Okay, anyone, any other answer? So to understand this, so let me give a hint here. So the hint is, what does the percentage s specifier? So how will your what will your printf function do when it sees this percent s format specifier? Yeah. So when you pass a percentage s, when it sees a percentage s format specifier, then it is going to print the string. So it is going to print the string. So it is going to uh, read the values, and it will keep reading until it encounters a %0 and then it keep printing. But for doing so, what is put on the stack? So, so what it is, so in case of this particular printf here, it is going, so this is the format specifier %s. So corresponding to this %s, it is going to use this byte sequence which is put here. It is going to use this as a address of the string, right? So it basically parses the different kinds of format specifiers in different ways. Like if this is a %d, then it is going to take the value which is written here and print that value. In case of a %s, it is going to take this value and use it as the address of the string. And then it will print from starting from that address until it sees a 0, until it sees a null character. Now, in this case here, when you have these %s sequence, now what is the possible outcome of this program and why? So in this case, it is going to use these arbitrary byte sequences which are there on your stack, and it is very likely that these byte sequences will not be a, like there's so many %s here, and it is possible that these byte sequences will not be a valid address. Okay, so because these are usually, like say, the data variables which are stored on your stack, and so the data values, and these data values will most likely here, if they form a valid address, if this is already say a valid address, then it will start printing from that address until it sees a null character. But it is highly likely that this value here will not be a valid address, and in that case it is going to crash the program. So it is going to cause a segmentation fault. Is that clear? Yeah. So that's right. It's going to cause a segmentation fault. So, so we have looked at this format string vulnerability, and now we looked at like it can cause a segmentation fault, right? Next, what we so now what we can also do with this is we can crash the program. Okay. Second, we can print the content of the stack. We can print the what is there on the stack. And for that, all you have to do is that print this format string. Sorry, give this format string which has say %x. And then your printf is just going to take this and start printing your stack content. %x here means that you want to print in the hexadecimal notation. Okay. And then you can not only so you can even like print any arbitrary memory location also. Okay. So so for example, here you were like printing only starting from this, and then you will print only above and like this. But you can even print any memory location with by crafting a format string. Okay, so for this particular example here, let's say that your program has this global variable, static global variable, which is S, which is a buffer of size 1024 byte. And in this buffer, let's say that you have stored some secret message. Okay, and then inside the main function, and this S is actually not going to be say used inside this main function, but without using this S inside the main function, you can actually print the content of S. without even specifying the argument, without even specifying the address of S here as without even specifying the S as argument, the name, the string name here S as the argument to printf, you can print the content of the string. So for doing so, let's say that we create a user string and it's of size 100, and it is say local variable in the main function. And we what we are going to do is that we are going to uh, fill this user string with a format specifier. Now, here in this example, we are doing it currently with str copy, but it can be filled by other means as well, by like taking user input or by reading the network packets, etc. So the attacker basically can say like craft a this format string which is being passed to the printf function. And this printf function, we are first here storing the address of this string s. Sorry. In this format string here, which we are creating here, we are first storing the address of s. Okay, we are first storing the address of s in little Indian format. Then we have placed here some percentage x's, and in the finally we have placed here a percentage s. And if you will use here the right address of this string s, the right address of this string s, and if you will you like take this code and if you will run it, then of course with a little bit of like tweaks here in this format string, you will be able to print the content of this string s. Okay, and so let's say you take this, then you compile it, and then if you run this binary, then you will be able to print the content of the stack, and you will be first you will be able to print some content of the stack, and after that you will be able to print this secret message. Now, why is it possible? So it is actually here possible because you have first here placed the address of this string, then you have this percentage x's and followed by a s, and this percentage s is going to pick the this address which is you have specified in the beginning, and it is going to start printing from there. So it will become a bit more clear. Uh, Yeah, so now we are going to see it here and it will become a bit more clear. So let's say this is your string, yeah, this is your string S. And let us say that this your string S is stored at this memory location 80496C0. Okay. And what you're going to do is that you're creating this format string, okay, where you have stored this address in this format string in the little Indian format. So it is stored like 0xC0, then 96, then 04, and then 08. After that, you have percentage x 1, 2, 3, 4, 5, 6 times, okay, and then you have a percentage s. So then let's look at it here. So let's say that this is your stack and this is your user string. Okay, here, this is your user string, which has this content 80496C0, which is the address of this string. And after that, you have this percentage x's followed by percentage s. So this you are passing to the printf function as the argument. Okay, and now let's look at it here. So now this is going to be your pointer inside this. Now this is going to be your pointer inside the format specifier, because you're passing the user string as a format specifier. So this is actually a local variable, right? This is the local variable in your main function. And then this is your so when then you are going to say call here printf function, and then the printf function is 1 second, 804856. Yeah, so actually you have not provided any arguments here. So you have not provided any argument here, right? I mean, you have only passed it to the printf, only the format string and no arguments. So when then this is the pointer P is pointing to the user string, because that is your format string. And then argument pointer is pointing, say here. So when you had called printf, but you have not passed any arguments here. So let's say the argument pointer is like just uh, just like above the pointer to the format string. Okay, it's located just above the print, like in this example. Yeah, right. In this example here. Yeah, like in this example, when you just passed a format string here, you have not passed any arguments here. But when there is even no argument, and this is how you had, I mean, there is only one argument, which is the pointer to the format string. And then these percentage s's, when the printf is going to parse this, then it is going to start picking the values from the stack. So that's how it is going to proceed even now here. So let's say that the argument pointer is here. This is the and the format string is there in your main function, right? It's been passed from it's stored here. So then the printf will start to read this user string, because it's the format string. It is going to start reading it. Then the first time when it sees this value A08096C0, then it is just going to print it. Okay, it is just going to print it, and it's going to take this value, it's going to print it, because that's what your printf does. If it sees any other value except percentage, it's going to just print it. After that, it is when it sees percentage x, it's going to read from the stack, and it is going to print the values there on the stack in the hexadecimal notation. So it is, let's say it is going to print this value 8048566. So that value will be printed. After that, in the next percentage x here, it is going to this argument pointer is moving up, even though I should emphasize, even though you have not passed any arguments to printf except the format string, printf is picking anything from the stack by in sequence. Okay, it's printing values from the stack. So when it is the next percentage x, it is going to pick up this value, and then it is going to print that. So 1a is printed. Then so on, it prints the next value on percentage x, and so on. So finally, we have, so you have crafted, say you have put here, you had put here, say 6 percentage x's. Why 6 percentage x's? Because initially your AP was here, your argument pointer was here, and there were six locations in between. So you have put 6 percentage x's. So once these six percentage x's have been printed after this, sorry, yeah. So after the 6 percentage x's have been printed, you will reach in the format specifier. You will reach the format specifier percentage s, and at that time your argument pointer will point to the first value which you have put in your user string. So when you were crafting this format string, then in that format string you have put the address of this location that you want to print. In this case, the address is of the global string. Okay, so you have put that address here, and then printf is going to you see at this format specifier, it is going to see that okay, this is percentage s, so I should use this value as an address, and then I should start printing from this address. So this string is located at this address 80496C, and it is going to start printing from here, and that then you can see that value on your as an output. So this is how you can like use this format string vulnerability to print an arbitrary memory location value. Okay, you can use this percentage x's to get a dump of your stack, and you can use this percentage s to start printing from any location, and then the printf is going to print until it sees a null character. So I will just go over the steps here. Uh, so printf, it is for this particular example that we have seen. In this particular example, we are also going to see the same example in the demo as well. But here we have first created a global string s, which is say the top secret message, and then inside your main function you have this character buffer of size 100, which is a local variable in this main. Let's say this user string buffer you are then filling, and you are filling it with this sequence, like you're filling it with this format string. In the beginning of this format string, you have put the address of the string s in the little Indian format, and then after that you have these format specifiers percentage x 6 times and then percentage s, and then you are calling printf function here and passing this user string. Okay, so the printf function is actually called with this format string, and when this printf function is called with the user string, then printf will start to read the user string. Right from here, the pointer p, which is inside the format string, will be initially located here, and the argument pointer is, let's say, pointing here, which is like just above the pointer to the format string. And then whenever it sees a format specifier percentage s x, it is going to read the argument from the stack, and then it is going to print it, and then it is going to increment this both of the pointers p and ap. So here, if we have sufficient x's, percentage x's, and then we will eventually reach the first value in the user string. That we will eventually reach this value. And then at that same time, if we are at percentage s in the format specifier, then the percentage s is the printf is going to treat this value as an address, and then it is going to start printing from this address until it sees a null character. So that's the format string vulnerability and the format string exploit. Now let me see if there is any question. So is it clear? Or if you have any question, then let me know. Yeah, so the 6x's here is actually the it's similar to when we were looking at these buffer overflow attacks. So to find out how many percentage x's you have to use, you will have to look at the stack content or the stack layout or the instructions, and then you will have to see how many bytes is your is your AP and P pointers are away. So that you will, it's like so you will have to, similar to the attack exploits which we were doing in buffer overflow, this is also program dependent. So it's not fixed here actually. But why particularly for this example sequence what we are seeing here, why 6 um, here with if let's say if this is the layout, then y6 is because initially your AP was here, and whenever you see a percentage x, then you're going to print the value here. So initially your AP was here. Once what? Yeah, initially your AP was here, and when your P is here, it sees the pointer P is here, it is seeing percentage X, so it is going to print the content at AP, and then the AP will be incremented. Then P is also incremented, then it is going to print the next 4 bytes. Then so on, it is going to print the next 4 bytes. So next after this, there are also like 3 percentage X's, which will print these next 3 4-byte locations. Finally, after printing this 6 percentage X's, you will finally reach percentage S pointed to by P, and the this location which is containing the address of the string pointed to by AP. And then if printf parses this percentage as format specifier, it is going to use this as the address of from where it should start printing. Does that answer your question? Yes. So the address 80496C0. Yeah, so it's first. Yeah, so correction, it is 80496C0. It should be 80496C0. Yeah. So yeah, to find the address of the string 80496C0, you will have to uh, check it at runtime in your program. Like, what is the address of this string? Like, where is this string located? Yes, it is program dependent and also depends on each invocation of the process. In case ASLR or some ASLR like mechanism, if it is enabled, then it will also depend on each process launch, because even the address that you are interested in can be randomized at each time. Is there any other question? Okay, so let's then look at the next very interesting thing, which is more format specifiers. So we have so here looked at very interesting format specifier, which is this percentage X. Okay, next look at another interesting format specifier, which is per percentage and $S. Okay, so actually for this particular example, what we saw earlier, here we had to put here 6 percentage X's, right? So but there is a better way to do this. Like if you don't want to say put here percentage 6 X's, like actually 7. Yeah, if you don't want to put here percentage 6x followed by percentage s, then you can use this syntax also. You can write say percentage n then $S. So then it is going to pick the 7th argument from the stack. But that's just uh, I mean, that's just another way to do the same thing. It's not new. Now, what we are going to look at next is to how we can. So in the last exploit, we looked at how we can read an arbitrary location. Okay. And now we are going to look at how we can overwrite an arbitrary location. Okay. So for overwriting an arbitrary location, we are going to use this format specifier, which is the percentage n. So can you tell me, uh, okay, it's written actually here only, that percentage n format specifier returns the number of characters printed so far. Okay, so can you tell me in this example here, what is this example going to do? Can you tell what is this code going to do? So the percentage n format specifier is going to return the number of bytes which have been printed so far. Okay, why 6? Okay, what this is actually going to do is, so format percentage and format specifier returns the number of characters printed so far. So in this case, printf would have printed 1, 2, 3, 4, 5 characters, and then it sees a percentage n. So 5 characters have been printed. And after that, here actually in the argument, we have passed percentage I, which is the address of this integer I. So what printf is going to do is, it is going to fill the value pointed to by this address, that is the integer I here, with value 5. So it's going to fill I with value 5. It's not going to print uh, here. It's going to place this, although actually I'm not, uh, it's possible that it may be printing, and that I am not sure about this. But what it is going to do as a side effect, if even if it's printing, is that it is going to take the number of bytes, number of characters that it has printed so far, and it is going to put that into integer I. So it's going to fill I with 5. Now, using the same approach that we just discussed to read data from any location, we can modify printf, and we can modify any location using printf. And so this can be used to change the function pointer values also. Okay, and now 1 second. But before, let's say, if before I move forward, can you tell me, yeah. So can you tell me, can you leak? Can you leak stack canary value using the format string vulnerability? Yeah, so that is right. So because as we were looking here, so if you just you just use this percentage x's, like basically you can pass any long, you can pass this format string of any length, right? It can have many percentage x's, and so then you can basically print the content of the stack, and your canary is also stored on the stack, so you will be able to see the stack canary. And so let's say if the function foo is calling this printf, then you will be able to see the stack canary, which is preventing the return address from the foo function. Okay, so then let's say after the printf, uh, then you will, so with that you will be able to say inspect what is the value of the stack canary, and then you can say try to use that in an exploit. If the if that function is also taking any input from the user. So the stack canary can be leaked, or actually in fact any data which is being stored on the stack, that can be leaked. So the function so that like the not just on the stack, but any data for which the value, for if you know the address of that data, and you can use that address and you can print that value. So it's like breaches this confidentiality. Now we are going to look at that, can we uh, overwrite an arbitrary location in the program, and in that way we will be able to breach the integrity. So integrity means that we want to prevent the value of some location, let's say. We want to prevent the attacker from changing the original value of some data. Okay, so that data of interest can be, say, your function pointers, and it can be your return addresses, etc. So the format string vulnerability can also be used to change these function pointers, return addresses, as well as any other data also in your program. And you can fill this, you can change this data in with arbitrary values. So how can we do that? We can do that, of course, by using this percentage %l format specifier, as we just saw in very simple example here. What is it doing? It's doing, what it is doing is that it is going to uh, store the number of characters that have been printed so far into the variable I, okay, into the location here. Now let's try to overwrite arbitrary location with some number, okay. So then let's say this is the arbitrary location, which is like this s here, which is an integer, and it's a global integer, and we want to modify it. So initially here it is 0, its value is 0, and then we will be able to modify it with some value. And so to do so, we have first created a user string, okay, again a character buffer. Then in that user string, we are first going to place the address of this integer s, which is here 804096, sorry, 08 0496C0. So that is going to be your address. After that, we have this percentage 08x, percentage 08x, and so on, and then the percentage n. So can you tell me what is this percentage 0x, sorry, 08x is? What is this percentage 8x? What does that mean? So what does a percentage, if you would have used it in your C programs, or if you have seen it, then what does percentage n d or percentage n x, what does it do? Octal value. Okay. Do you, I'm not very sure. Do you mean similar to like hexadecimal? Then you're printing the values in a octal value print. In that, like in some particular format. So actually, it is a width specifier, which means that how many bytes should be used for this value. So here you are saying that use 8 bytes. Okay, use 8 bytes, and you have to print it in the hexadecimal. So it is going to print whatever there is on the stack. It is going to print that in the hexadecimal format, and it is going to use 8 bytes for this. So if the value is say only even one, if your value is say only one in your hexadecimal value is only say one, then also it is going to use this 8 bytes by by filling the leftmost most bytes as 00. Okay, so it's going to be like 00 followed by 7 more 00s and then 01. So that's how it is going to write on back. Now why are we using this? Because otherwise, let's say, so this only this particular percentage 8x itself will be counted as 8 bytes written by printf. Okay, so when we write this percentage 8x, so that means printf has written 8 bytes. Now can you tell me that what will be, how many bytes will be printed by the printf starting from here till percentage n? So there are these 1, 2, 3, 4, 5, 6. 6%, so yeah, 6% 08x is here. And then there are these 1, 2, 3, and 4 bytes here. So this is actually 8 times 6, which is 48. Uh, yeah, so this is 48 bytes printed plus 4 bytes. So that will be 52 bytes. So total 52 bytes will be printed. And then this percentage n will contain, sorry, 48 plus 4 bytes will be 52 bytes. And then this percentage n will be 52. And after that, if you have this printf user string, then it is going to store 52 value into this s. And if you will print this percentage ts, then you will see that the value of s is now 52. And even though you have not set the value of s is equal to 52. So in this manner, you can change the value of the some address. Okay. Now a simpler way to do the same, like so of course you can simplify it further. Okay, you can just use some, instead of writing so many percentage 08 x's, you can just write say percent 53 x's. So then it will print 53 bytes, and then these 4 bytes etc., or some 4 bytes more, and then that value will be stored. So then you will not have to write so many times. So because you can specify this width specifier. So the width specifier can be even like as much as like 1000 or 2000, 5000. It can be basically anything, any value. So that gives you the flexibility to write any value into the this into the address here. Okay, so you can add any arbitrary number basically here. Of course, this number plus these bytes. So that you will have to take care. Now, you can even use percentage hn. So let's say if you want to store a very large number, and you want to store, let's say it's like a long or something, then if you want to store a very large number, so then in that case what you can do is you can fill that number in these 16-bit sizes as well. And so you can fill basically 16 bits at a time. So what you can do is, for that you have to use this percentage hn. So it is going to use only 16 bits. Okay, it's going to use only 16 bits. And so it will first, so whatever the number of values that so whatever is the number of bytes that you have printed, that is going to take, and then it is going to store at this address. So you are here providing the address of first 16 bits, lower 16 bits, and then you are passing the address of the higher 16 bits. And then you are passing here percentage hn, percentage hn, and so then you can store actually 16-bit and then 16-bit values like this. So these are basically like the options that this format specifier is providing. So what you can achieve with format specifiers. So but so in conclusion, what this percentage n allows you here, and this is actually very similar, it will work in the same manner that we see for reading the percentage, for reading the value, for reading that string, top secret string. It is going to work in the same manner. It's like these 6% x's were placed such that then when you reach at the end of this format string, then you will be at this at then I mean the percentage x's also have been similar to here. The 6% x's were there because so that when you reach percentage n in writing one, then you will be your AP, your argument pointer, will be pointing to the address which is stored in your string, which is stored in your string here. So both of the attacks, they are working like writing to an arbitrary location or reading from an arbitrary location. They are working exactly in the same manner, except that we are using a different format specifier. Here we are using a percentage n, and we are relying on the fact that the percentage n is going to take the number of bytes that have been printed by printf so far, and it is going to take that, and then it is going to write that into the address which is pointed to by the argument pointer. And then we looked at that the width specifier gives us the flexibility to choose an arbitrary number to write into this location, into the arbitrary location. So here we can choose an arbitrary location, we can choose an arbitrary number, and we can write that. So that's the format string vulnerability and the format string attacks, exploits that can be used to read an arbitrary value, and it can be used to write an arbitrary value, such as you can write a return address, or you can write the function pointers, etc. So now the question, is there any question? Is there any question regarding this, or is it clear? So now the first question is, if you think about in terms of W XOR X, uh, will you be able to prevent the format string exploits with W XOR X? Yeah, so W XOR X does not prevent the format string exploit because we are not trying to execute any code. We're just reading or writing. Uh, okay. So then the second question is, what about stack canaries? So here we just saw that with format strings vulnerability, also we can write arbitrary value to an arbitrary location. So we can change the function pointers or return addresses. All we have to do is that all we have to do is that we have to pass the right address here where we want to write. Like if we want to change the return address, then we have to pass here the location of return address, and we have to write the correct number of bytes, and then we have to fill the bytes correctly. Of course, it's or we can fill in this manner like arbitrary values one by one. Okay, and we can give addresses here, let's say. So So we can then try to say corrupt the function pointers or with the return addresses. Now the question is, will it be prevented with stack Kennedy? Yeah, so it is not going to overflow the buffer, and it is not even going to uh, touch the stack canary. It is just using any arbitrary location here. It's just any location that you want to write. So we're not overflowing the buffer. We're just using some arbitrary location, and then we are going to try and write this there. So then stack canary can also be subverted with this. Now, what about ASLR? If you have an address space layout randomization, will be that be able to prevent this kind of an attack? Like, will it be able to prevent the return addresses from a modification with such attack? Yes, that is also absolutely correct. ASLR is going to make the exploit difficult because then it will say change the layout of the change the base address of the stack every time. It is going to add random padding between the stack frames, and so then it is going to, or between the buffer and the return addresses location. So then it is not going to uh, so it will make it harder to exploit. But yes, it's not a foolproof solution because if the layout is not changed, let's say, and if the attacker is able to guess the location of the return address on the stack, then it can still do this. So it's still not a foolproof solution. So now let's take a 15 minutes break, and let's start at 4:30, and then we will start with the demo for format string vulnerabilities. After that we will look at CFI and then CFI and then memory bound checking. Okay, if there is any question, then please leave them on the chat. I will take them when we are back. So now let's meet at 4:30.